All right, hello everybody. Sorry that I'm not here today and tomorrow, but this is the calm before the storm that is basketball season for me. So I am taking a long weekend and headed to Florida with the fam. So I'm on a sunny beach. You, however, are in a classroom ready to learn some calculus and some derivatives. Here's what you need to know for the next 2 days while I'm not going to be here. Today's just going to be notes. Two 15-minute videos to watch. That gives you time to pause, rewind as necessary, and that's all you do today. Tomorrow is the day where you're practicing what you're watching today. So don't just watch the video. Talk about it at your tables. Pause if you need to. Look at some of the examples that I'm going to do. But we're moving into some shortcuts that will really make the derivative process a whole lot easier. Because what we've been doing is we've been finding derivatives using limits. Using this definition, let's go ahead and jump and look at the notes. We've said that the limit as the change in x gets infinitesimally close to 0, that then f of x plus delta x minus f of x over delta x, we can use this formula that's kind of like a complex slope formula, and we can find then the instantaneous slope using that formula. That is the definition of a derivative. But as you know from last night's homework, it takes a lot of algebra to do. So let's review. The derivative represents the slope of the tangent line. Okay? And it's the tangent line because if we're looking for average rate of change, let's just look at something like this. Average rate of change, you would just pick 2 points and find the average rate of change. That's a secant line. But we want the instantaneous rate of change, so if we just want the slope at that particular point, we need to find the slope of the tangent line to the curve. Okay? So derivative just means slope. There are multiple notations for derivative. The first primary notation that we'll use is f prime of x. It looks like f of x just with a little tick mark. Same is true for y prime. It looks like a y equals, but just with a tick mark. And then one that's less common, but we'll still use quite a bit, dy over dx, change in y over change in x, the derivative of y over derivative of x, that we need to be comfortable with as well. So we're going to learn 4 main shortcuts. We're not going to do the trig at the bottom, but we're going to do 4 main shortcuts that you can apply to almost all derivatives, all the basic ones at least, and then we'll do some examples, and that'll be the end of this video. So here's the first rule that's going to save you guys a lot of time. These just need to be memorized. You might notice the patterns already from what you've been doing, but this is just going to put it in writing. So this box here is crucial for this video. The first rule is if you ever have y equals and then just a constant. So y equals a number. I'll put an example. Y equals 4. Anytime you need to find the derivative of this equation, aka an equation that would help us find the slope at any point, that's what a derivative does, is it finds us the slope at any particular point. Well, let's imagine what that looks like on a graph. Y equals 4 would look something like that, right? A horizontal line. Well, what's the slope at all those points? The slope at every single one of those points is 0, and thus our first rule is anytime you have y equals a constant, the derivative is always 0. That's rule number 1. If you ever take the derivative of a constant, it's 0. The derivative of a constant is 0. Say that in your head 6 times and then move on. Okay? Next rule. We've got if you have y equals a number and then x. An example, just so it looks more normal, is y equals 4x. Okay? If you ever need to find the derivative of a linear function like this, just with a slope and an x, the derivative is always going to be equal to whatever that number is. Let's think about it graphically, and I'm not going to show a graph on all these, but you need to understand what's happening here is if you have the line y equals 4x, there's a rough sketch. What's the slope at this point? It's 4. What's the slope at this point? It's 4. What's the slope at this point? It's 4. So that's why then the derivative is just telling us no matter what point you choose, the slope is 4. Just like it told us in example 1, no matter what point you choose, the slope is 0. All right, here's where things get a little more complex. What if you had y equals x to some power? So x squared, x cubed, 3x to the 4th, 7x to the 6th, right? Here's what the rule tells us. It tells us that the derivative is going to be equal to, you're going to bring the exponent down front, and you're going to subtract the exponent by 1. Now this notation might be intimidating, but literally I hope you see what we're doing. We're bringing the exponent down front, and then we're subtracting the exponent by 1. An example would be this. If I told you to find the derivative of x to the 3rd, then the derivative would be, bring the exponent down front, so 3, subtract the exponent by 1, so 2. So the function is x cubed, the derivative is 3x squared. That's what that rule tells us. Okay? And then the last rule just gives us the ability to put all this together, is what if you have a function like y equals, let's say 3x squared plus 4x. Notice how there's two pieces on this. Okay? The rule just tells us that you take the derivative of each individual piece. So actually I just wrote the example. Let me write the rule here. The rule would be if you ever have y equals and then you have f of x plus g of x, so two multiple pieces, then the derivative is going to be the derivative of the first piece, notice f prime, plus the derivative of the second piece, g prime. So y equals 3x squared plus 4x, the derivative then, you would just take the derivative of the first piece. So what is the derivative of 3x squared? Well, let's bring the exponent down front. That would make 6 because they have to multiply. And then we subtract the exponent by 1, and that would leave us a 1. Plus, what is the derivative of 4x? Well, rule number 2 tells us that when you take the derivative of just a 4x, like a linear function, then you're just left with the 4. So the function was 3x squared plus 4x. The derivative was 6x plus 4. Now's a good time to remind you, what does the derivative do? The derivative helps us find the slope, aka the instantaneous rate of change, at any point on the graph. So you know what this would look like, don't you? I'm hoping you know it would look like a parabola, a quadratic graph. So the slopes change. A parabola looks like this. Sometimes the slope up here would be negative, sometimes the slope over here would be positive. So the slope's always changing. This function will help us calculate that. This particular derivative is paired with this particular function. Okay, they work together. That's what the derivative does, is it helps us find the instantaneous rate of change. Okay, we're at the 8-minute mark. My cheap free video software only lets me do 15-minute videos. That's why the first one didn't work. I just filmed a 17-minute video for you guys, and then it told me, you can't upload this because it's too long. So now I'm redoing it. So let's skip down to the examples. We'll talk trig when I get back. Okay? Let's look at some examples. This is where you really need to focus because there's a 3-part method to solve all of these. And yes, they're simple, but if you don't do this method, you are going to be lost. I promise you. This is not my first time teaching this stuff. Okay? So when you see this equation, f of x equals 1 over x, and it wants us to find the derivative, we don't have a rule for when an x is on the bottom. So we look up here and we're like, which rule are we possibly going to use? Well, here's what you have to do with these. And I'm going to do this for example 1, 2, 3, and 4. You have to do what's called the rewrite phase. First, we have to rewrite it before we can find the derivative. Okay? So step 1 is the rewrite phase. Step 2 is going to be the differentiate phase, which is just a fancy word for find the derivative. So we're going to rewrite it, then we're going to find the derivative, and then a lot of times we then have to clean it back up and simplify. Sometimes some negative exponents might appear, or other fractions that we might need to move around, okay? So here's what I mean by rewrite. I'm going to use red. We can't find the derivative of 1 over x. But couldn't I rewrite the function instead of f of x equals 1 over x? What if I rewrote it as f of x equals x to the negative 1? Now it's in a form that applies one of our rules. Which rule can we use? Rule 1, 2, 3, or 4? I'm hoping you said rule 3, where when we have something to the power, x to the negative 1, when we need to find the derivative, we can bring the power down front and subtract the power by 1. So notice that negative 1 came down front and I subtracted the power by 1. But we don't want to leave an answer like this with negative exponents. So we're going to do the final stage, the simplify stage, and say that the derivative equals negative 1 over this x to the negative 2 just goes to the bottom and becomes positive. So that is our derivative. Pause this video, rewind if you need to see that example again, but I need to move on for sake of time, okay? So example 2, we're going to start with the rewrite phase, then we're going to do the differentiate phase, and then we're going to simplify, okay? I want you to do your problems like this today and tomorrow. When we get back, we might not show this every time, but you need to start, okay? Trust me. So, do we have a rule that has a quantity raised to a power? We do not. I'll scroll up here for you. You have your notes on paper, but look, we don't. Nothing about a quantity to a power. So when we rewrite, we need to rewrite this. We need to actually go ahead and do 2x cubed, which would give us 8x cubed as our function, right? So then now we're ready to find the derivative of this. So y equals, instead of 8x cubed, we bring the exponent down front. And since there's an 8 already there, we have to multiply. So bring the exponent down front, subtract by 1. And that looks pretty good. There's no simplifying needed. So our final answer then of our derivative is 24x squared. Next one, square roots. You already know the drill. We don't have a rule that covers square roots. So is there a way that we can rewrite it? There is. We can change this to y equals x to the 1/2. So you're going to get in the habit of changing square roots to 1/2, changing cube roots to 1/3, etc., etc. Okay? Because now we can find the derivative, and we can say that the derivative of this is bring the exponent down front and subtract by 1, which 1/2 minus 1 is negative 1/2. But obviously we can clean this up. So our final answer is this x to the 1/2 is going to go to the bottom, and you can either write it like this, or if you want to have a little more math swag, you can write it like this. It means the exact same thing. But then we can't leave off the 1/2, so we put the 1/2 back. So that is the derivative of the square root graph. Okay? So what we're doing, I think now is a great time to remind you, do you remember all the work we did last week where we had to do f of x plus delta x, and we had to factor, simplify, cancel, etc. to find the derivative? Well, these are just shortcuts. But what we just found is the derivative in 3 simple steps using these shortcuts. Okay? Last example here. Number 4. Again, x is on the bottom. We don't have a shortcut for that. So we have to do some form of rewrite. Then we'll differentiate, and then we'll simplify to clean it up. Okay? So the rewrite phase, instead of 4 divided by 3x squared, watch close because everybody messes this up. We want to write this as 4/3 times x to the negative 2. Pause the video and let your brain sink in on that, on what just happened, because it needs to click for you. Okay? So that is the same thing. These two things are the same thing. Notice the 3 stayed on the bottom. So when we differentiate, we bring the power down front, which would make negative 8/3. We subtract by 1, and now we're ready to simplify. Our final answer is x to the 3rd on the bottom because it's negative, but we still have a negative 8 and a 3 as a part of our answer. Okay? In video 2, we're going to look at some more complex examples, review our rules, and also talk a little bit about tangent lines and what they mean. Watch this video again if you need to. If not, move on to video 2.